Welcome to GATE tutorial on electrical engineering subject. Today we will discuss about circuit theory. In GATE exam, the syllabus for circuit theory is given here. The whole syllabus for circuit theory will be discussed here in different parts. First, today we will discuss circuit theory in part 1. In part 1 you can see here that we will discuss this thing. These are the topics which are we going to discuss. The basic concept part, the circuit elements, Ohmic law, Ohm's law and Kirchhoff's law, and Nodal and loop analysis. In basic concept part we will start from charge, current, potential difference, power, etc. Then we will discuss the circuit elements, that means circuit elements that resistance, inductance, capacitance, and active elements, passive elements, and ideal voltage source, practical voltage source. All these things will be detailed and discussed in this circuit element part. Then we will discuss about the very basic of circuit theory, the Ohm's law and Kirchhoff's law and load and loop analysis. So let's start from our basic concept part. First we will discuss about charge. What is charge? Charge is an electrical property of any atomic particle which actually the matter consists. The unit of charge is coulomb. Unit of charge is coulombs. That means the charge is measured in coulomb. There are two types of charge. Two types of charge. One is positive charge, another is negative charge. An object is said to be positively charged. An object is said to be positively charged if it has excess proton. Otherwise, if it has excess electron, then it is negatively charged, and if it is uncharged, then both these two charges are present in same equal quantities. Then come to our second part, which is current. What is current? Current is the flow of charge. Flow of charge is the current. Flow of charge is the current. If current I and charge is Q, then I is equal to dq dt, or in integral form Q is equal to I dt. Current measured in ampere. So ampere, the unit of current, I, A, ampere is equal to charge by time, second. So unit of charge is coulomb. So coulomb per second. Ampere is equal to coulomb per second. There are two types of charge. Two types of current: DC current and AC current. DC current is that which remain constant over time, and AC current is that which varies sinusoidally over time. Now next to our come to our next part, which is voltage. Voltage or potential difference. What is this voltage or potential difference? Potential difference or voltage is always measured between 2 points in any system or within any system, and this voltage is defined as the energy required to move an unit charge through an element is termed as potential difference. That is, energy required to move an unit charge through an element is known as potential difference or voltage. Now, voltage VAB between 2 points A and B is defined as the energy required to move one unit charge from point A to point B. Unit charge required to move from point A to point B. That is the potential difference or voltage VAB. Now, this VAB, according to definition just I said, is equal to energy required to move one electron, one unit charge through an element, which is in mathematical term is defined as VAB is equal to dW dQ, where this W is the energy measured in joule and the Q measured in coulomb before we saw. So that potential difference or voltage measured in volt is equal to energy, unit of energy joule, unit of charge is coulomb. So volt is equal to joule per coulomb. Now we have an element here. This is point A, this is point B. This is at positive potential, this is a negative potential. Now, in this case, potential difference between this point AB is denoted by VAB. Now, this voltage or potential difference VAB greater than 0, meaning is that potential at point A is higher than potential at point B, and if this VAB less than 0, that means VAB, then we can say, or actually the case is, potential at point B is higher than potential at point A. This plus sign and minus sign we basically use for the reference direction, or basically the polarity of the potential. This positive signs means the point A is at higher potential than point B, and this VAB meaning is that potential at point A with respect to point B. So this is all about potential difference or voltage. Now come to our next part, that is power is the time rate of expending or absorbing energy. This power measured in watts. That means the unit of power is watts and denoted by W. Power P is equal to unit of power is W denoted by W, and the power is denoted by P, which is equal to the time rate of energy expending or absorbing energy. So time rate of change of energy, P is equal to dW dt. Now this dW dt we can write it as like this: dW by dq dot dq dt. And this the dW dq is the voltage. Previously I just told voltage, and dq dt, charge flow of charge, is current I. So power is equal to voltage into current. Now this power may be in absorbing power or supplying power. What is absorbing power and what is supplying power? Let's start. Let's try to understand. Say we have an element and point A, this is point B, and current is flowing through this element, which is I, and the voltage between these 2 points is V. Okay, let's another element, say here there are also point A, point B, and voltage between them is V. In this case, current is coming out from the element. In case of first element, the current you can see here is entering the element. That means this voltage is driving the current into the element. So this element is absorbing the voltage and current multiplied, which is power P, absorbing the power P into I, P into I, and this is positive power. P is equal to P into I. This is the absorbing power, absorbing power. And here in this case, P is equal to minus Vi. Since this is current coming out from the element, and this is called supplying power. Okay. Law of conservation of energy must be followed. So total power, summation of total power is always remain constant through any element. Okay. In the definition of power, we just seen that P is equal to time rate of energy, dW dt. So energy W will be integration of power over time, and this P is equal to voltage into current. So B into I. So total power is equal to B into dt to I. Next, our last concept part is energy. Energy, you can see, you know already that what is energy is defined is actually the capacity to do work. Energy is the capacity to do work. And energy, which I told that they are measured in joule, that is the unit of energy is joule. Capacity to do work is the energy. Next, we will discuss about circuit elements. What is circuit element? So, circuit element. Circuit element. A circuit element is a two-terminal device. Circuit element is a two-terminal device which is completely characterized by current through that element or voltage across it. Total current elements are grouped into two categories. Current elements are grouped into two categories. First is passive element. Passive elements. So what is passive elements? Passive elements are those which are capable of receiving power or storing power in it or return it to the external circuit. Passive elements, what are the example of passive element is resistance, a resistor I think, and capacitor and inductor. All these is passive elements. Another one is our active element. Active elements. What is active element? Active elements are all types of energy source which are capable of generating or delivering power or energy to some external devices. All type of energy source are active elements. Active elements is example for batteries. In electronic circuit, op-amp, also generator. All these are active elements. Now we will discuss first about the passive elements, and the basic passive elements are resistor, capacitor and inductor. So we will discuss first about resistance. Definition of resistance already we know actually. It is basically the property of any material by virtue of which it offers opposition of flow of current, and by doing so it converts energy into heat energy. You also know that the resistance is defined basically from the Ohm's law. What is Ohm's law is? Ohm's law is defined or tells us that when temperature remains constant through an uniform cross section wire, the potential difference V is directly proportional to the current flowing through that wire. Potential difference is directly proportional to the through the any element when temperature remaining constant. Now this proportionality form we can write V is equal to I into R, and this R is the constant of proportionality, is known as resistance of this wire or element. Now the resistance, this resistance of any material depends upon different factors. What are the factors? Type of the material first. Type of the material. Resistance depends on the type of the material. That means different material have different resistance value. Then length of the material. Resistance value also depends upon the length. Then cross section area. Cross sectional area. Normally we write it like A, and this is L. And next, our final part, which is one very important part, is temperature. Resistance depends upon all these factors. Say we have an wire conductor, say, the cross sectional area is A, and the length of this conductor is L, and rho, which is called the resistivity. This material having resistivity, material of the conductor having resistivity rho. Then for this conductor, resistance is defined as R is equal to rho L by A. Also, I just told that the temperature have a great role on resistance. So resistance in terms of temperature effect, R, say temperature at T, any temperature, any value of T is equal to R, say 0, 1 plus alpha delta T. This rho is the resistivity of the material, and the unit of this rho is ohm meter, SI unit. A CGS unit is ohm centimeter, and this R0 is the initial value of resistance, or it may 0 degree, resistance at 0 degree, or room temperature value, or say at 20 degrees C. And this alpha is known as coefficient of resistivity. The inverse of this resistance is called conductivity. Conductivity is denoted by G, and which is inverse of resistance, that is 1 by R. Unit of resistance is ohm, so in unit of conductance will be mho. It is also known as Siemens. S symbol. Now Ohm's law, in Ohm's law we have seen V is equal to I into R. Now this I, in definition of charge, we have seen this I is the flow of charge. So this Ohm's law can also be represented in terms of charge, which is equal to R is equal to dq dt. V is equal to R dq dt. Ohm's law in terms of charge. I have just said that the temperature has a great role or great effect on resistance value. The resistance value increases with temperature. When it is the case, then we said that material is positive temperature coefficient of resistance. When with the increase of temperature, resistance value of any material decreases, we said that the material is negative coefficient of resistance. Now, in terms of resistance, the power equation can be right. In power equation, we know V is equal to P is equal to V into I, and this V is equal to, from Ohm's law we have just seen this I into R, and this into I is equal to I square R watts. Now this power P is equal to I square R. This is a normal equation, but in terms of conductivity, just I told this is G, inverse of resistance. We can write it out. Say P is equal to V into I, and this V I, you can see in terms of conductivity is V square into G, or it is equal to I square by G, since I is equal to Vg. Now we will discuss about resistance in series and also in parallel. What is the equation actually? No, we are not going through the details about it. Simply we will write it down in the form of equation. And you already know that the resistance in series are in series. Say like this. So in infinite number of resistances, say we have resistance here, another resistance is here, another resistance is here, and so on, infinite number of resistance. Series connection is this, just simply connect it from end to start, and so on, like this. And this is the series connection of resistance, and the value of resistance R1, it is R2, and R3, and so on, it is Rn. If this is the case, then equivalent resistance in series connection R equivalent will be sum of all the individual resistances. This is R1 plus R2 plus R3 plus Rn. And resistance in parallel, which is like this, each individual resistance are in parallel. Just connect end to end and write down. This is our R1, this is our R2, and this is Rn. If this is the case, then the equivalent resistance in parallel circuit is, the equation is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by Rn. This is the equation for parallel connection, and this is the equation for series connection of resistance. Our next passive element after resistance is inductance. Inductance. First we will try to define inductance. Now we know that a current carrying conductor produces a magnetic flux which links through it. So current, whenever flowing through any element, a magnetic flux created and linking through it. So that magnetic flux phi is proportional to current I, and this conductor or anywhere having n turns, if having n turns, then in terms of turns we can write that n phi is equal to L into I. This L is called the inductance. Okay. Now from Faraday's law we know already that a voltage is induced in any coil if there is a rate of change of flux, and that Faraday's equation we can write induced voltage V is equal to N d phi dt. Okay. Now this phi is equal to L I by N. Put this value of phi here. So this comes N d phi dt, and this value Li by N, which will be L di dt. So voltage is equal to L di dt. P is equal to L di dt. You see that the voltage V is equal to L di dt. This is the differential form. In terms of integral form, we can write it down like this: I over time t, time independent, is equal to 1 by L integration minus infinity to plus infinity V dt. Now this part we can break into two parts, that is minus infinity to 0 or 0 to infinity. So 1 by L minus infinity to 0 V dt plus 1 by L 0 to infinity V dt. You see that this part is the initial value of current which flows through this inductor. That means we can say that an inductor has a past history. That means initially it has some value of current, and this whole term is, we can write I at 0, initial value of current, and that value I, that is remain as it is, P dt, and the current I is equal to over time t is equal to this. This is the current equation through any inductor. So in terms of equation form, this equation in terms of schematic diagram or diagram, we can write it like this. This is an inductor and this is a current source. This is the current, initial value of current, this value I 0, and in current flowing through this inductor, this is 1 by L 0 to infinity V dt, and this is our total current, right? Okay, we have just seen that the voltage V is equal to L di dt. So power through an inductance P is equal to V into I. Now put this value of V here, which will be L I d I dt. This is the value of power equation, P is equal to Li di dt, and energy P is equal to dW dt. From this we can write it P dt and put this value of P, this value of P, that is this, in this equation, which will come I energy is equal to half L into I square. So our energy through, or energy absorbed, or energy through any inductor, W is equal to half L I square. Okay. From this equation shows that inductor store energy, and it given back to the circuit when current value becomes 0. Okay. Now another case, we will discuss about another aspect of inductance. Inductance also depends upon the relative permeability of any material, and also it is inductance is inversely proportional to the length of a magnetic path. In that case, the inductance value L can be written in the form of permeability of any material, like this: mu 0 mu r n, number of turns A by L, length of the magnetic path, where this mu is equal to mu 0 mu r is the permeability of the core. Already I have just seen that n phi is equal to Li. Okay, so put that value of L here, which will be mu n square A by L into I. And this n will be cancelling out, only one n will be remain, so phi will be is equal to that mu n A I by L. You can write in terms of arrange value is that mu A by L into this n I. Okay, now what is this n I? This Ni is the MMM, magnetomotive force. It is also known as ampere turn, simply AT. Okay, so MMM or ampere turn, from this equation what will be? Phi L by mu A, or in terms of arrange value you can write L by mu A into phi. Ampere turn is equal to L by mu A into phi. See this equation, write it down again. Ampere turn is equal to L by mu A into phi. This part, especially this L by mu A, is called the reluctance of the magnetic circuit. Reluctance of the magnetic circuit. Which is similar to the resistance of any electric circuit. It is equivalent to resistance of a electric circuit. This L by mu reluctance is denoted by S. And so S reluctance is equal to L by mu A. Now this opposite of reluctance value, that means inverse of reluctance, which is 1 by S, is equal to mu A by L, mu I by L, is known as permeance. This is called permeance. This is known as permeance, and this unit of this is ampere per Weber. Okay, so this is the unit of permeance is Weber per ampere per Weber. Now we have seen that the voltage through any inductance, from Faraday's law we have seen V is equal to L di dt. Okay, now see from this equation, this inductance is proportional to the rate of change of current. Now this current, when reaches steady state value, that means this current remains constant over time. In that case, this value is vanish. That means the voltage is nil. So current steady state means what? DC current. So in case of DC current, inductance, voltage across inductance is 0. Voltage 0 means what? Short circuit. So in DC circuit, inductance simply becomes short. Now that is the case in case of the direct current, DC current, the voltage through inductance is 0 and it comes at a short circuit. Now before in case of resistance we have seen that in series connection resistance is equivalent to sum of all resistance, and in parallel connection another equation I have said. But here also for inductance L in series, same relationship holds. That means equivalent resistance in series connection will be summation of all the inductances. And for L inductance in parallel, similar relationship hold as in case of resistance. That means 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by Ln. Next we will discuss about capacitance. What is capacitor actually? A capacitor is a form of two parallel plates and a dielectric medium in between them, and the capacitance is basically the measure of a capacitor's ability to store charge in its plate. So capacitance is a measure of capacitor ability to store charge in its plates. If V voltage is applied between the two plates of a parallel plate capacitor and charge is Q, then Q is proportional to the voltage applied across the plates, and the Q is equal to C into V, where the C, which is the constant of proportionality, is called the capacitance. This capacitance value depends upon the geometry or the shape of any dielectric plate, the two charge plate and the dielectric medium. For two parallel plate capacitor, the value of capacitance C is equal to epsilon A by D, where that epsilon is equal to epsilon 0 or epsilon R into is equal to dielectric constant. Dielectric constant. Now, a current charge, current definition of current, we have said that the current I is equal to dq dt. Okay, so put that value of q is equal to cv in this equation. So we will find like this: dy dt, put that value c and v. Now see, the C capacitance is remain constant over time, So C is equal to dV dt. So current I is equal to C dV dt. Earlier we had seen that the inductor becomes short circuited in case of DC circuit. That means when current flows, steady state current flow. Now in this equation you see that when voltage across any capacitor, this voltage reaches to steady state value, that means constant value, then this term becomes 0. So current will be 0. So when voltage reaches steady state value through a capacitor, current becomes 0. And what does this mean? Current becomes 0. That means the circuit is open. So in case of DC circuit or constant voltage circuit, the capacitors current across capacitor is open circuit. The capacitance become open circuit. So in earlier case we also in case of inductance we also write in integral form. Here we can also write about the integral form of the voltage across capacitor, and which is V is equal to 1 by C integration minus infinity to plus infinity, and this is I over time t dt is equal to, we will separate into two parts as before, minus infinity to 0 I t dt plus 1 by C integration 0 to infinity, so maybe t value, say I t dt, and this value is the initial value of voltage across the capacitor. And when we switch on any system, then the voltage before switching on and after switching on, both voltages will be equal. So for in that case, capacitor voltage across capacitor before switching on, which is denoted by negative value, will be equal to capacitor voltage, initial voltage after switching on will be same. So in this case, the voltage across the capacitor equation can be written B is equal to B C0 plus 1 by C integration I dt. So this equation in terms of circuit we can write like this, that this is our capacitor and the initial voltage V, this is the value of the capacitance charge value 1 by C integration 0 to t I t dt, and the value of initial value of resistance is this, which is Vc0, and total voltage is Vt. Okay, as before, power in a capacitor P is equal to V into I. We have just seen that this I is equal to C dV dt before that. So V is equal to P is equal to B into C dV dt. and as before power also dw dt, and that is w is equal to integration p dt. So w is equal to this p value, put it this p value here, so integration vc dv dt into dt, which will come as w is equal to half c v square. This is the energy equation of a capacitor. The energy is stored in a capacitor. In this equation you can see that the energy stored in a capacitor only depends upon the value of the voltage. Okay. Next, capacitance in series. C in series. We are not going in details about this, we simply write it down, the equation for series connection or capacitance. To remember the equation, it is the very inverse equation of resistance or induction in case of resistance or inductance. So equivalent of capacitance in case of series connection will be 1 by C1, 1 by C2 plus 1 by CQ, Cn. And for capacitor in parallel, it will be the summation of all the capacitances. C equivalence is equal to C1 plus C2 plus C n value of capacitances. So we have seen that in the passive element cases, resistance, inductance and capacitances. Inductors and capacitors absorb energy for t greater than 0, and that energy returns to the source when switch is off. Okay, so for we have three types of equation: voltage equation, current equation and energy equation. And we have three elements: circuit elements. First, resistance. In case of resistance, voltage equation. What is this voltage equation? Simple equation, which is V is equal to IR. And current equation, just divide it, right? I is equal to V by R. And the energy equation or power, which is P is equal to I square R. For inductance, inductor, voltage equation, Faraday's law, L di dt. Previously we have seen. And current equation, I is equal to 1 by L, 0 to infinity, or say t value, any value of t, infinity value or t value may be v dt plus initial value of current. And the energy equation or the power across this, W is equal to half L I square. Okay. And for capacitance, capacitor value, what is the voltage equation? I have just seen V is equal to initial value voltage plus 1 by C integration dt it dt. Okay, and the current equation is I is equal to C dV dt. Energy just in W is equal to half C V square. This is our basic relationship between the passive circuit elements and their voltage equation, current equation, and energy equation. You have to remember all these equations every time, because these are the basic concept just we have to remember.